Hi, Ivan.
Hi, Professor Chu.
Oh, I see you in class today. Nice seeing
I
you.
just decided to join.
Okay, let me see if I can get my video to work right. Okay, it works better now. Hi, David and Michael. Nice seeing you here.
Hello.
Let me see. This is about time to get started. Can you all turn on your video camera so that I can see your faces? Hi, Michael. Hi, Jason. Let me put on my earphone. Hi, Jing Liu.
Morning, Professor.
So let me see. Can you see my screen?
Yes.
Yes.
Okay, wonderful. You can see my screen. And today I'm going to talk about shielding and image theory. It's an interesting topic because you need to understand this kind of shielding and image theory for many different applications, especially in the field called EMI and EMC. Stands for electromagnetic interference. Put an E. And the EMC stands for electromagnetic compatibility. Okay, and this happens for a number of reasons because the cell phone industry is driving this. You have about maybe 6 billion transistors in the cell phone, the expensive one. You have 6 billion transistors. In the cell phone. You can imagine how tightly packed the electronic components are. And you like to get them not to interfere with each other as much as possible. And sometimes this could be very difficult, so you have to resort to different kinds of clever engineering. And this field is very much driven by heuristics. Okay, so it's really difficult to do mathematical analysis, but we use heuristics and physical insight. To drive this field, okay? Let's see how we can understand this field heuristically. Let's take the example of 2 conductors. And if you have 2 conductors that they are placed somewhat like this, and that the conductors are oppositely charged. So they are positively charged on this side, whereas this other conductor is negatively charged on this side. Then the picture of the electric field will look something like this around this conductor, okay? And I guess the figure is a little bit distorted. It looks a little bit better when it was printed out. But on this picture, it's a little bit distorted. But what happens is that the electric field is 0 inside this conductor, and both of them are 0. And I'll explain to you why the electric field has to be 0. The reason is because if the electric field is not 0, say if it's not 0, if E is not 0, then J is equal to sigma E is not equal to 0. Then there will be current flowing inside this conductor. And that is not electrostatic shielding, because we want to talk about electrostatic shielding as to what happens in the static regime where nothing else is changing. The only possibility for this to happen is that E has to be 0. Otherwise, we have a contradiction. Okay, so E has to be 0 inside so that J is equal to 0. And also over this side, J is equal to 0. And then only would you have a quiescent state. Let me see if I know how to spell quiescent state. A quiescent state means nothing is changing. Okay, and that happens when the positive charges try to produce an electric field that is 0 inside, and then the negative charges try to produce an electric field that is 0 on the other object. And if the electric field is 0, that means that no current is flowing and you have reached the static regime. Otherwise, you will never get to the static regime. If the current keeps flowing and flowing, the current will produce a magnetic field, the magnetic field will produce an electric field, and so on. So you will never be in the static regime if the electric field is not equal to 0. So the only possibility is for the charges to cancel the total electric field inside. Say if there's an electric field coming from the other conductor, it tries to penetrate into this conductor, then negative charges will pile up. Negative charges will pile up in such a way to make the E field equal to 0 here. And similarly, if this negative charges produces this electric field, positive charges will pile up on this end so as to produce 0 electric field inside. That is called electrostatic conductor shielding, and you can understand the physics quite well. So you don't need a perfect electric conductor, okay? So no PEC for electrostatic shielding. Just need the conductor. You just need the fact that sigma is larger than 0. That is good enough to produce shielding. However, this is for statics. And if the sources are time changing in state, like what we see here, if this is a dipole source, and this dipole source is a Hudson dipole, say, driven by some sources where you have currents flowing between the two spheres, then this electromagnetic field coming from this dipole is changing. And in this instance of time, when this is positively charged, this is negatively charged, then it has to be such that there will be negative charges on this side of the conductor. Okay, this is a conductor, this is a dipole. This is just a conductor. Okay, and then as the dipole is time varying, it will come to an instance where this is true, this will be negatively charged, the other one will be positively charged. Then what happens is that this part of the conductor will become positively charged. So you can only go from scenario 1 to scenario 2 if there is a current going back and forth. Okay, here the current might be flowing in this direction, and over here the current might be flowing in this direction. So a time-varying electromagnetic source like a dipole, could be a Hertzian dipole, produces time-varying electric field inside the conductor. So electric field is not zero anymore. Electric field cannot be zero. However, you can show that the electric field has a penetration depth, very much like the skin depth. And we have earlier looked at the skin depth formula, that the penetration depth of an electromagnetic field into a conductor surface is proportional to this depth. There we did a very simple closed form example using plane wave. But this intuition still holds true, that the non-zero electromagnetic field will confine themselves to a very thin layer close to the surface of the object. Another thing to notice is that the charges are moving back and forth. So they have to have time to relax from one mode to the other mode. So the charges have to relax from this mode to the other mode. And there's a relaxation time involved. And this is very much similar to an RC tank circuit. Say, if I have a resistor and then I have a voltage source that is time varying. Okay. Then the charges will go back and forth between the two sides of a parallel plate capacitor. And then there will be a time involved called the relaxation time. The relaxation time is the RC time constant. Okay, and it will take longer and longer for the charges to relax themselves if R is very large. And also, if C is very large, this relaxation time will also become bigger. And you can actually solve this problem in closed form. I'm sure that you have solved this problem before. Okay, and that you will find that the voltage in the current, I, is proportional to something like this. If you switch it off, if you were to switch the current off or the voltage source off, and if you have this, okay, you take the voltage source away and then let some current flow in this circuit and ask yourself, what time does it take? How long does it take before the charges go away? Because eventually the charges would disappear due to dissipation, and it goes away within this relaxation time. And also there is a relaxation time associated with a conductor, and that relaxation time is proportional to roughly epsilon over sigma inside the conductor. So it takes about this kind of time scale to relax from one mode to the other one. And you can see that this is very much like capacitors per unit volume. And then this is conductors per unit volume. So they have actually the same dimension. And if sigma is very, very large, okay, then this thing goes to zero when sigma goes to infinity, which means that if you have perfect conductors, perfect electric conductors, it takes no time for the charges to go from one mode to the other one. It takes zero time, which means that the conductors are very good conductors. It takes no time to move the charges back and forth around this thing, okay? So we come to an interesting demonstration of a Faraday cage. A Faraday cage is just a cage where you have wire meshes. You can actually make a cage out of chicken coop wires. And there could be very, very big holes on the side of the cage and on the top of the cage as well. And as long as you ground the cage, and you know that if you have a constant potential, if you have any surface where V is a constant, then the E field has to be 0 inside. Okay, very much like this case over here. In the first example that we showed here, essentially if E becomes 0 inside, then grad phi must be 0. Which means that phi is a constant inside the conductor, and then phi is also a constant inside this conductor. This means that inside the conductor at the electrostatic frequency, or in the electrostatic case, the potential is always a constant inside this conductor. And if you go and look at this case again, what you have then is that if this cage surface is kept to be equal potential, having a potential which is constant, then the potential must be the same, uniformly a constant inside, and there will be no electric field inside. So by such a very simple design, you can force the electric field to be 0 inside this cage. And of course, this is close to electrostatic case. So, but however, if the electromagnetic field is slowly time varying, say if you have an electric field or electromagnetic field coming in, and if that electromagnetic field is slowly varying in time, it still very much would look like an electrostatic field. And hence you can see in this picture, this lady is well protected by this Faraday cage, even though this person is trying to attack her with a very high voltage source. The high voltage source cannot penetrate into this Faraday cage. Okay. Are there any questions regarding this electrostatic shielding and quasi-electrostatic shielding? Okay. So these problems are hard to solve. For instance, if I were to ask you to find a solution of this Faraday cage problem, it becomes a very difficult boundary value problem. However, there are certain problems where we can solve in closed form using image theory. An example of a closed form solution is that case of a static charge on top of a conductor. Okay, let's see how we can solve this problem in closed form. Well, even on a conductor surface, we know that n cross E has to be 0. Okay, n cross E has to be 0 because, as we said before, in a static case, E has to be 0 inside. If E has to be 0 inside, tangential E has to be continuous. It means that n cross E must be 0 on the surface as well. Okay, so if you look at the electric field, they actually look like as if they have been normal to the surface. This picture is not that well drawn, but this should all be normally incident on the surface. Okay, so if that is the case, how can we construct a solution such that the electric field is normal to the surface? We can do this by using image theory, by saying that, well, I can add the negative charge. I can take the conductor away. I can take this conductor away, and then add a negative charge over here. And by this principle of linear superposition, I can see that this electric field produced by the positive charge will look something like this. And then the electric field produced by the negative charge will look something like this. Okay, and if you add the total electric field produced by these two charges at the interface, then it only has a horizontal component because it only has a normal component. Okay, the electric field must be normal to the surface. The horizontal components cancel each other, as you can see from this picture. So if you were to draw the picture of total charges produced by the linear superposition of positive and negative charge, you can see that they produce no tangential component of the electric field at this interface. In other words, the electric field produced by this problem of a positive charge together with a negative charge has the same form as the electric field of a positive charge on top of a PEC surface, or not necessarily PEC, just a conductive surface. Because by the principle of linear superposition, the electric field produced by the two charges would cancel on this plane. Okay, so this is the simple use of image theorem to find a closed form solution due to a point charge on top of a layered medium, or not a layered medium, just a conductive half space. Then we go to the case of a dipole. The rule is very simple. The rule is that whenever we have a positive charge, its image is a negative charge in order for the boundary condition to be satisfied. Then if we have a dipole, we can look at the positive charge first. The positive charge will reflect itself with the negative charge in image theory. And then the negative charge part of this dipole will reflect itself to be a positive charge. So the image of this dipole is a dipole of opposite polarity. Okay, this is the dipole. And the one below definitely is a dipole of opposite polarity. You can see that it's pointing in the wrong direction or opposite direction. However, if you have a vertical electric dipole, usually this is called horizontal electric dipole. And this is a case of a vertical electric dipole. And the positive charge will reflect to a negative charge down here. A negative charge will reflect to a positive charge down here. You can see that a vertical electric dipole reflects to a vertical electric dipole of the same polarity on this case. So this is opposite polarity. And this is of the same polarity. Okay, so you can use image theorem to find the static solution of a electric dipole on top of a conductive surface. But then this is using static theory. The image is quite easy to find. What happens if you have a conductor that is not static? If you have a conductor that is imperfect, okay, then in the static case, the electric field will still be completely shielded out. But if this is time varying, if this dipole becomes a horizontal dipole where the currents go back and forth, then as we said before, the electromagnetic field is not zero below anymore. So this image theory does not apply. It only applies to the electrostatic case. What happens if you replace this half space with a perfect electric conducting surface? As we say, we have the case where the relaxation time goes to 0, which means that if you have a time-varying Hertzian dipole, for instance, up here, then the conducting surface, which is a perfect electric conductor, can respond immediately to the time-changing dipole. Okay, its response time is 0, and it will follow the switching sign of the dipole upstairs. And similarly, this would also be switching in its sign, and the one that is below, if this is a perfect electric conductor, would be able to follow the thing on top. So this image theory, when omega is not equal to 0, still holds true if we have a perfect electric conducting surface here. Okay. So are there any questions regarding the image theory for electric dipoles on top of a conducting surface? Okay. If you don't have any questions, let's move on to the case of a magnetic dipole. Okay. This is a tricky case because there are no magnetic charges. This one fundamental thing that we know. And another fundamental thing that we know is that if we have a PEC, N dot B has to be 0. Because if we have a PEC, it has to be such that E has to be 0 inside the PEC, and B has to be 0 inside the PEC. Okay, it is not stable for B not to be 0, because if B is not 0, then by Faraday's law, if the B field is going to be changed just a little bit due to vibration or some agitation by thermal noise in the environment, if there's only going to be a little bit of change in B, it will produce an electric field. And if it produces an electric field, then there would be a current flowing in this conducting medium. But we are assuming that sigma goes to infinity. Sigma is infinitely large. So a small amount of electric field will produce an infinitely large current. And then by Ampere's law, the infinite current, okay, will produce a magnetic field. So this goes to infinity, and then J would produce an H that goes to infinity. So the whole process is not stable. You see that if there's a small amount of electric field or magnetic field inside the conductive medium, it will produce infinite current. The infinite current in turn produce infinite magnetic field, and that will give rise to an unstable situation. So the only way for the electric field and the magnetic field to exist inside a perfect electric conductor is for both of them to be zero. So the electric field and the magnetic field, or the magnetic field due to a magnetic monopole, this is the B, okay, and it will have to satisfy the n dot B equal to zero on this surface. So the only way that you can get n dot B equal to zero is to have an image that is of the same polarity as the original source. And if you add the two fields together, then you can see that n dot B equal to zero. So the image theorem for a magnetic monopole over a PEC is quite simple. It reflects to itself over a PEC surface, okay? So then we can go and do this for magnetic dipole. And again, you can put for instance, a magnetic dipole here, a magnetic dipole here to make this. And because over a PEC surface, it reflects to itself. Okay, so a horizontal magnetic dipole reflects to a horizontal magnetic dipole on a PEC surface. And again, by the same argument, you can actually show that if I have a magnetic charges here, these are magnetic charges. Then because they always reflect to themselves, so the charges here will be negative and positive. So if you have a vertical magnetic dipole, you will produce a negative vertical magnetic dipole in the image theory if that surface is PEC. Are there any questions regarding this? So a vertical magnetic dipole reflects to something that is negative of itself over a PEC surface. A horizontal magnetic dipole reflects something that is the same as itself on a PEC surface. And this is opposite compared to the case of this is opposite compared to the case of electric dipole that we talked about earlier. Let me go and revisit that. And for electric dipole, the electric dipole reflects to something that is negative of itself, whereas the vertical electric dipole reflects to something that is the same as itself over a PEC surface. I just want you to remember these two very important points. Then we come to a very interesting phenomenon called the Meissner Effect. Okay, called the Meissner Effect. Let me see if I can. Maybe I can put this over here. Okay. The Meissner Effect is the case when you have a bar magnet put on top of a superconductor. This is a superconductor where the conductivity is infinitely large. This bar magnet is such that the North Pole is up there, and then the South Pole is down here, say. Okay, so in the magnetic field, the magnetic field of a magnet Okay, this is a bar magnet. Because we have a superconductor below, so the image of this bar magnet is actually something that looks like this. Okay, the south pole is down there, and the north pole is down there. Because this is something that we have learned from image theorem. If this is a perfect conductor, perfect electric conductor, which is the case when we have a superconductor, then this bar magnet reflects to something that's opposite of itself. Then this south pole will repel the south pole. Because of that, you will find that this simple bar magnet can levitate itself. This is called magnetic levitation. Okay, magnetic levitation. How many of you have seen this before in the lab? You have seen this before? Okay. I saw this in the Boston Science Museum the last time I went there in 2018. So I know that it's there in the Boston Science Museum. I don't know if it is in the Chicago Science Museum or Science and Technology Museum. You might see it there as well. Okay. So let's talk about PMC surfaces or mushroom structures. Okay. PMC surfaces will look something like this. There's no real PMC surfaces, but we can mimic PMC surface. Okay, mimic PMC surface. And how do engineers do that? Well, this is two guys by the name of Steven Piper and Bolonovich. They were clever enough to actually come up with this surface that looks almost like a PMC surface. And let me see how to spell the names. The names are Steven Piper and Norwich. Okay, at the time when they were doing this, they were at UCLA. Okay, so what you do is to make a mushroom structure. And if you look at the mushroom structure, it consists of a capacitor cap followed by a stem, which is an inductor. So you can think of this as being very much like a LC tank circuit. Okay, there's a capacitor and then driven by inductors, and this is the ground plane, and then you will have inductors and then capacitor and then inductors and so on. So you can think of the circuit equivalence of this structure to be something like this. Okay, it would be something like this, and at the resonance frequency, then I is equal to 0. There's no currents flowing horizontally in this structure. So if I is 0, then Js on this structure is 0. It means that N cross H is approximately 0 on this surface because there's no current flowing there. So this is just what we need for a PMC. PMC is N cross H equal to 0. And you remember that for PEC, it is the other way around, that N cross E is equal to 0. So this structure, if you operate it at the correct frequency so that all these mushroom structures start to resonate, they form open circuits up at this surface. This surface will look very much like a PMC surface. So that's how engineers design PMC surfaces. Are there any questions regarding this structure? Okay, if no questions, then let's go to the image theorem for PMC surfaces. We have so far talked about PEC surfaces, and we figure out how to reflect images on the PEC surface by using simple image theorem. And we also did that for electric dipole as well as magnetic dipoles, okay, which is what we have here. Electric dipole, and then we have magnetic dipoles. Okay, these are magnetic dipoles. And then we try to talk about the construction of a PMC surface using engineering. And this is roughly the case of a PMC surface. Then let's go and assume that PMC surface exists. Of course, it does not exist in practice. It can only be engineered approximately. Then if you go and summarize the image theory for a PMC by duality principle, okay, if you have a horizontal magnetic dipole, then it actually should be negative of a horizontal magnetic dipole. Very much like the dual of this problem, that if you have a horizontal electric dipole, it reflects to negative of itself. Okay, here, a horizontal electric dipole reflects to the negative of itself. This is PEC surface. By the duality principle, a PEC surface becomes a PMC surface. So when you have this, you can see that this reflects to negative of itself. And then by the same token, if this is a vertical magnetic dipole, it reflects to something that is the same polarity as itself by the duality principle. And by the same token, if you go through the argument with the electric dipole, if you have a vertical electric dipole, then it will become the negative of a vertical electric dipole. And if you have a horizontal electric dipole, it is the same as its original self. So are there any questions regarding the use of image theory to find simple solutions? Okay, so if there are no questions, I'd like to move on to working on a case where we have multiple images. And if we can use multiple images to solve some complicated boundary value problems, such as this one over here. We have used image theory to solve a very simple problem involving, say, a positive charge over a PEC surface. And by argument, physically, we say that a positive charge has to see an image which is negative of itself. Okay, this is a PEC. And of course, if you have a PMC, the opposite happens. So if this is a PMC, you have a positive electric charge, then it should see a positive magnetic charge. Okay, and then you can do the same for a magnetic charges. Okay, so we're going only to talk about electric charges here. We're going to talk only about electric charges here, and then you can use image theory quite easily to say that if I have a positive charge, let's assume that this plane is infinitely long. Okay, this plane is infinitely long, and this is a PEC surface. Okay, then I can quite clearly see that the boundary condition is satisfied. If I have a positive charge, if I put a negative charge there, then n cross E must be 0 on this surface due to the fact that I'm just using image theory. But by symmetry, I can also see that this problem of putting the 4 charges in this manner also satisfies the image theorem for this surface over there. So I can see that n cross E is also 0 on that surface, which means that by the use of 4 charges, I can make n cross E over to be 0 over the entire angular surface or 90-degree surface I have here. Okay, so this is one use of image theorem that is beyond a flat surface. I can do the same thing for a more complicated surface like this one over here. And again, I can put this positive charge and negative charge there. And I put a positive charge and negative charge, and first think of a PEC surface over there. Okay, and then I can start to add, for instance, so you have this set of charges. I can add the images, like I can add this one, which is the image to this one, and then I can add this one, which is the image to this one. And then I notice that I can add this one, which is the image to this one. Okay. Then I notice that the boundary condition is also satisfied on this surface over here. Okay. And then I can see that the boundary condition is such that n cross E has to be 0 and n cross E has to be 0 on both these two surfaces. So by symmetry, you can see that by a judicious placement of the positive and negative charges, you can produce a problem where n cross E equals 0 on the surfaces that you have desired. Okay, this is only possible by using symmetry. So if the problem is not symmetrical, then there's no way you can find such a solution. Okay? So you can find a solution such as this one, you can find a solution such as this one, and maybe some other problems where you can have a certain degree of symmetry. Another problem that can be solved in closed form by image theory is this problem over here. And you can see that once I put a positive charge there, I have to use a negative charge if this is my only plane. And then I can also put in a plane here fictitiously to begin with. And if I were to put negative and positive charges over there, I can see that boundary condition on that thing is still satisfied. Okay, and you can keep putting images up and down. You can find that finally you will find that boundary condition is equal to 0 on both surfaces. Okay, boundary conditions will be 0 on these surfaces. Okay, so this is just a very simple use of image theory. And however, there are some more complicated problems where you have a positive charge next to a sphere. Somehow this thing does not appear like a sphere to me on my computer screen, but it's supposed to be a sphere. Okay, so if you put the positive charge here and a negative charge here, and if you adjust its location, the location of this negative charge properly, okay, the picture is not very well drawn, but it should be something that is actually symmetric. Okay? If you put this positive charge and the negative charge at the correct location, then you can actually work out a solution where n cross E equal to 0. Okay, I'm not going to work out the details for this problem, but it has been worked out in Ramo et al. Okay, I can even give you the page number, but the page number is given in the lecture notes. And you can go through the mathematics and find the location of the negative charge such that the two charges together, the positive charge and the negative charge, would produce electric field that cancel each other on the surface of the sphere. And you can also repeat this for a cylinder. Okay, just a lot of mathematics. Okay, but it turns out that this problem is also solvable. That is, if you have a dielectric interface, a positive charge over there and a negative charge over there, and if you pick the strength of this image charge to be given by this thing over here, you can show that the boundary condition is satisfied on this surface. What is the boundary condition that we should have on this surface? It's not the PEC now. Okay, what do you think are the boundary conditions there? It's an electrostatic problem. So what are the two boundary conditions that we should have on that surface? Okay, anybody wants to suggest the kind of boundary conditions we should have at that surface? So if it is an electrostatic problem, we only need to solve two equations, okay? The two equations that we need to solve are divergence of D equal to rho. And since there's no charge except for plus charge over there, okay, so we don't have to worry about rho except for this point over here. The other equation that we need to solve is Faraday's law. But since this is static, Faraday's law just become that. Okay. So now if you eyeball these two equations, what are the boundary conditions that follow from these two equations if you have to solve them? What is, maybe you go with the simple one. If you have Faraday's law for this problem over here, what is the boundary condition that you should have? Anybody? Well, we learn how to eyeball a PDE and actually very quickly determine what the boundary condition should be. Would anybody like to tell me what the boundary condition should be if I just eyeball Faraday's law and ask myself what the boundary condition should be at this interface? Let me see. If you're not going to answer, I'm going to call your name. Okay. What about Jason? What do you think is the boundary condition I should have for this Faraday's law?
Is it the tangential electric fields are equal?
Yes, tangential electric field continuous. Very good. N cross E continuous. So you have N cross E continuous at that surface. Okay, you should have this continuous. There's one boundary condition. What is the other boundary condition? We would have to solve Laplace's equation, because if you were to solve this equation, then E is equal to minus grad phi. And then D is equal to epsilon E would be epsilon grad phi. And then from this equation, you will have divergence of D would be minus divergence of epsilon grad phi equal to rho. Okay, so those are the two equations that we need to solve. And actually, the second equation looks almost like Poisson's equation, except that it is more complicated than that. Okay. However, if you assume that epsilon is a constant in this region and epsilon is a constant in that region, then the Poisson's equation actually becomes like quite simple. Divergence of gradient of phi is minus rho over epsilon naught in this region, and divergence of gradient of phi equal to minus rho over epsilon 1 in this region. Then you solve these two equations, and then those two equations actually follow from these two equations. Okay, they follow from these two equations, and they're second order PDEs. So they need two boundary conditions. So the two boundary conditions that you have told me are tangential E is equal to continuous. The other boundary condition is that the normal flux, or the, actually I haven't asked you about the other boundary condition. The other boundary condition that follows from this this thing, okay, that if I were to go from here to here, the boundary condition that it induces is D1, D2 is equal to surface charge. But there's no surface charge in this problem. Rho sub S is equal to 0 at this surface. So we can set this to be 0. And then the other boundary condition will be epsilon 1 E1 minus epsilon 2 E2 equal to 0. And actually we just have epsilon naught and epsilon 1. So it will be epsilon naught E naught minus epsilon 1 E1 equal to 0. So those are the two boundary conditions that we need to solve this problem. and then if you solve it, and it's quite difficult to do, but it can be solvable using image theorem. And you can actually put the image to have this strength, and it will produce electric field in the whole of space. And then you can put a source at this point, it will produce an electric field that is in the whole of space. You can add the two solutions together, and you will find that both of them together will satisfy this boundary condition. The other boundary condition is tangential E is good, continuous. Okay, tangential E is continuous, and that is the same as phi continuous. Okay, phi is continuous. You can actually show that the phi being continuous will ensure that n cross E is continuous, because E is equal to the gradient of phi, and if phi is continuous from this surface to that surface, it will ensure that tangential E is also continuous at that surface. Okay. I guess I'll stop here. Are there any questions before we quit? Any questions from anybody? Okay, no questions. I'll let you go. Okay, I'll let you go, and next time you can talk about something more interesting. And thank you all for coming, and keep safe out there.
Thank you, Professor.
Thank you.
Okay, bye-bye. Derju, welcome to Purdue University. I forgot to send you the link this morning.
Oh, it's fine.
I'll put you on the email list. Okay. You have a Purdue email right now, right?
Yeah, I sent you the email from my Purdue email.
Okay, I've put your email address into my distribution list, so that next time when I make any announcement about the course, you will get this. Okay.
Thank you so much.
I'll talk to you all later. Thank you.
Okay.
Bye-bye, and thanks for coming.
Bye.